And thank you, everyone. Hello, good afternoon. Welcome to day 2 of the Hydrology Community Practice Annual Conference for 2021. As I mentioned yesterday, these have become sort of a recurring tradition for our community practice. And it gives us an opportunity to expand on the topics that we don't get to throughout the year through our recurring meetings, and we have a little extra time to explore some of the science and other larger projects and issues that we've all contributed to over the year. So welcome everyone, and on the agenda this afternoon we have 6 presentations, including our guest speaker, Dr. Siminovich from Western University. Hopefully I got your name correct. I see you smiling.
That's okay, yeah.
Excellent. So my name is Michael Seneca, and I'm in Water and Waste Policy Branch in Alberta Environment and Parks, and I'm the chair of the Hydrology COP. And of course, the community of practice is a group of about 40 or so, give or take, hydrology and water quantity and other water resource-minded individuals across the department, Alberta Environment Parks, the Alberta Energy Regulator, and Alberta Agriculture and Forestry. So before we kind of get into it today, I thought I would first pause and stop to acknowledge that today's conference is taking place on the first National Day for Truth and Reconciliation. And just to note that it's a somber day in Canada for remembrance, reflection, action, and learning about the longstanding impacts of the residential school system. And just wanted to say that maybe in your own way, take some time to reflect on the history of the relations with Indigenous communities and the treaties respecting the land that encompass Alberta. So I wanted to acknowledge that today because I think it is really significant to have the first national holiday, national recognition. And with that, maybe we'll get into some of the particulars of the session today. Another acknowledgement I want to make, and gratitude the organizing committee that put this together. I get to walk us through it, but it wouldn't have happened without the support of these individuals. So Zahid Islam, Naba Adakari, Brandy Newton, Khaled Akhtar, Abdullah Mamoon, Hyung and Ernst Kerkhoven. So that is your organizing team for this year. Thank you very much. And a few other little points before we get started. You'll probably note that the recording has begun. We're recording these sessions. We're not requiring anybody to have their video on. Of course, you're welcome to. But as mentioned, if it's not necessary, it will save bandwidth and storage space on the recording. So, but it's entirely up to you. And some particulars about the question and answer. So Khaled will be moderating the Q&A for the afternoon. So please submit your questions into the chat box. And after each session, we'll go through the questions that have come in. And for the first session, Hyung is offering support if there are any tech issues through the session. And I'll quickly do a check-in and make sure I haven't forgotten to mention anything with the rest of the committee.
I think
No, you are good to go.
Good to go. Okay. Well, then, without further ado, I would like to introduce Dr. Slobodan Siminovich. Just let me find the biography here. My goodness, there's a lot of letters after your name. PhD, PEng, fellow of CSCE, ASCE, lots of accreditations there. Professor Siminovich is universally acknowledged as one of the world's leading authorities on the application of systems analysis to water and environmental management. He's advanced the understanding of water and environmental systems by providing decision makers with tools to support their sustainable management. He provides unparalleled contributions to global and local management of water that has improved the lives and livelihoods of millions of people worldwide. His work significantly impacts our understanding of system linkages between humans and built and natural environments that lead to sustainable water resources management and resilience as a new development paradigm. And he's going to talk to us today about rainfall intensity, duration, frequency curves and future climate scenarios. Take it away. Thank you.
Thank you very much. All these acronyms after my name are just the proof how old I am. And I am very thankful that you did invite me to participate in your day and offer a little bit of our kind of experience related to the development of the intensity, duration, frequency curves tool for incorporating the future climate scenarios into assessment and development of the tools, of the tool. The tool is publicly accessible. I am not completely certain how many of you had the opportunity to see the tool or use it. These are the ways how you can access the tool. Very simple registration, just to kind of provide a name, and the association leads you into the tool that may be of some value.
Sorry, Professor, to interrupt. Like, are you sharing your screen? Because we don't see anything.
Okay, I am in the presentation. I'm sorry. What, Khalid, lead me? What do I need to? I was doing the same thing.
So go to share, like share content, and then
I'm sorry.
no, that's fine. Yeah.
Now better?
Yeah, so
just a second.
Okay, thank you.
Now it's okay? Okay.
Yeah, now it's
I'm really sorry. So that's the title we covered, and these are the web addresses for accessing the tool. My plan for today was to provide you with a given amount of time. I can talk only a little bit more about the kind of methodology and very little about the kind of implementation, and that will be mostly the content of this half an hour. However, I did provide a larger stack of the PowerPoint slides that includes also the hands-on session as well as the discussion of the use of the tool. Most of my experience with the tool since its public release was communicating with the users, focusing on the use and how to utilize the tool and what is the best way to kind of navigate yourself through it. So I will answer the questions if you guys have, but the slides are also provided for additional learning. At the end, I'm also listing some of the publications that may be of assistance to those who are interested to go into a little bit more detail. So the tool is developed by my research group at the University of Western Ontario and supported by the Institute for Catastrophic Loss Reduction. I'm serving as the Director of Engineering Works with the Institute. The Institute is right now the hosting place of the tool. You see a number of names of people who actively participated in the development of the tool: Dr. Chardon, Mr. Sending, Dr. Gaur, Professor Srivastav. So they all contributed in different parts of the development or different phases of the development of the tool. Let me kind of provide you a little bit about the methodology. I suppose for this group of people, it's not necessary to go too much into impacts of climate change, but there is a very clear link between the increase in global temperature and the change of frequency, intensity of extreme events. And the concerns are basically within the municipal boundaries. This is where the kind of tires hit the road. rubber-hit roads. So issues related to the risk of floodings, water supply, drainage, and so on are all the issues that kind of require a little bit of understanding how to incorporate these changing conditions into activities, municipal kind of engineering activities that are involving assessment of extreme precipitation and tons of planning, design, and operations activities. IDF tool is being used in the past, and that's a very common kind of engineering tool that covers the frequency of extreme events for different return periods and intensities. On the right-hand side, on the top, you have a typical kind of IDF curve developed and available through Environment and Climate Change Canada. However, the kind of key assumption in these tools is that they are based on assumption of stationarity developed using the historical information, and relatively difficult to relate to potentially changing conditions in the future. And we are kind of aware of the very extreme events. I have the illustration with this bar graph, which is kind of showing for the Toronto station, what the 100-year is and what are the events that were happening, like, how intense the rainfall events were in 2013, which are basically putting us in a situation that we need to reassess what is the meaning of the 100-year, for example, precipitation event. Updating IDF curves is a very technical kind of task. Municipalities are in tremendous need. I was presenting very often on the impacts of climate change and how to bring the climate change into municipal engineering activities, and almost always was getting the requests and questions related to the IDF curves, modification or updating of these curves. And very clearly it was presented with the fact that internally the municipalities do not have the capacity nor the kind of knowledge, so how that can be, how can go over that hurdle. And that's, I think, what motivated this work and motivated the development of the tool. Everything started with a number of contracts we had with the City of London, for which we were developing the updated curves. And then the work was picked up by the Insurance Bureau of Canada that developed and utilized the tool for a number of locations across the country. And in the same kind of time, or the time framework, the Canadian Water Network came with a call for proposals for the application of knowledge, which I found to be a pretty good opportunity to try not to present the development or the science, but implement that for the practical use. And this is how the proposal was offered to a Canadian Water Network, supported with the ICLR as a also supporting party. The main objective for that particular initial proposal was development of generalized methodology for updating curves for climate change, under climate change, and the implementation of this particular methodology in the kind of web-based format. In February 2015, we finished work, and the first version of the tool was made public. And as you can see, we are currently running the version 5, trying to maintain and update the tool as the new information is available, or responding to the requests of the users community. A number of tasks and improvements in the tool were simply done by responding to the requirements and comments that we were getting from the users community. Users community is growing on a daily basis. The kind of initial idea was development of the tool that will be used by municipalities, but right now we have about just before this beginning of the session, 3,792 registered and active users, and the users are covering a really broad spectrum of people. The I think initial use was within the municipalities and various departments of various government level departments. Then we noticed very large number of consultants starting to use the tool, and most recently, I'm noticing number of universities or basically students utilizing the tool, probably indicating that in some of the courses that they are taking, the tool has been introduced and used. I'm not going to spend, sorry for too many words on this particular slide. I just wanted to kind of give you the impression how the development of this particular tool went, because it had a very strong public engagement component. Obviously, early work on the City of London and then the Insurance Bureau of Canada was kind of providing us with the opportunity to publish and present the methodology and get some feedback. And in the same time, as I pointed out, the Canadian Water Network can, with that knowledge mobilization call that we responded to with the support from many municipalities across Ontario, Toronto, City of Toronto, Mississauga, Hamilton, London, Kingston, and so on, provided very strong support, and I think that probably helped approval of the funds by the Canadian Water Network. So from the point when the project was funded, we started working with the municipalities, trying to basically tailor the tool to help them in the activities that they indicated they need a tool for. At the beginning, we were working with the Toronto and Hamilton on a regular basis, Toronto representing a large municipality, Hamilton representing a smaller one. And then after the kind of first beta version was developed, we shared it with multiple communities that supported our proposal to get some feedback. And then followed with the 3 national workshops, East, West Coast, and Central Canada, to give opportunity to people in the, in these localities to join and learn about the tool. We also tried to run the national webinars, and it was an amazing experience. I must tell you, we hired a company that offered, opportunity for 100 participants, not expecting that we are going to get that big crowd. However, about more than 200 people tried to join that webinar, and the whole system crashed. So we needed to kind of repeat, and we did successfully organize that webinar for a very large number of people across the country interested in the tool. And that was the moment, or after that was the publication time, or publishing time, sorry, and the communication continued through basically questions, answers, comments, and feedback provided by the users directly through the tool. This is the timeline of the tool development. The first version used 24 global climate models, the Gamble distribution, the same that's being used by the Environment and Climate Change Canada for the development of the IDF curves, and original quantile matching algorithm for basically combining the observations with the future predictions of the GCMs to kind of modify or update the curves. I'll talk a little bit about the algorithm in a few slides. Second version was a little bit of a kind of improvement in the response from the users community. We replaced the interface, interface Google Maps were limiting, so we moved into leaflet and created a friendlier interface for the use. We also added 2 bias-corrected global climate models provided by the Pacific Consortium, Climate Consortium, that were basically developed for the use in Canada. And also we did some modifications of the methodology by limiting the use of Gumbel only for the historical IDF curves so that they can be compared with curves published by the Environment Canada, and the introduction of the generalized extreme value distribution as a better distribution for fitting the extreme precipitation for the updating process. That required modification of the quantile matching algorithm because the GEV is a little bit, different distribution, 3 parameters and so on. Third version was a response to outcry from the community for the ungauged locations and development of the curves for ungauged locations. And that required, completely different approach. We developed the methodology for ungauged locations. We incorporated the methodology into the kind of second part of the tool. So right now the tool is capable of doing both things, providing updated IDF curves for climate change for gauged locations as well as ungauged locations. I'll try to give you a little bit of a kind of methodological ideas about both of the methods. The fourth version in 2019 included addition of 24 new bias-corrected models from the PKIC, so expansion of the basically model base. And the last version was the version was published end of July of this year, basically included 30 new climate models from the coupled model intercomparison project 6, which was serving for the IPCC assessment report 6. These models are using different emission scenarios. They are using so-called SSP, shared socioeconomic pathways, that are in addition to RCPs, which were, the scenarios used with the CMIP5, providing some impact of the social activities on the future of the changing climatic conditions. The Environment Canada and climate change data set was also updated in the last version. They provided new precipitation data up to 2017. Some new stations were introduced. Some stations got the name changes and IDs changed. So this was all kind of updated and incorporated in the last version or the current version of the tool. Okay, a little bit about the methodology for the gauged location. This is the kind of entrance into the tool, which is kind of giving you opportunity to see or enter the tool through the a part that deals with the gauged location or the ungauged locations, and also provide a lot of information about the tool, about the modifications, about the versions, all the publications that are supporting the methodology, as well as the user and technical manuals. Currently, the tool includes 78 climate models. 30 are the new models added in July from CMIP6, 24 GCMs that are developed for CMIP5, and 24, bias-corrected, statistically downscale bias-corrected method provided by PKIC. So altogether, pretty large database of climate information is right now stored and available in the tool. I'm not going to go into details in the mathematics. I mean, 30 minutes is not allowing us to kind of go into these details, but fitting distribution to, Gumbel or GEV, I suppose, is very common in the hydrology community. So the Gumbel probability distribution is only preserved because Environment Climate Change Canada is using it for the development of the IDF curves that they are publishing. So we wanted to actually convince the users through the use of the same methodology, same data, that the tool is producing the same kind of IDF curves. So you have opportunity through the tool to develop the historical IDFs on your own, and you can do the comparison with the published Environment Canada curves. GEV distribution was introduced because it was a kind of consensus within the professional community that it is, definitely better fitting the observed extreme precipitation data. It is a distribution with three kind of parameters: location, scale, and shape, and we utilize the L moments in kind of estimating the parameters and fitting the GEV, distribution. This is the kind of graphical presentation of the kind of quantile matching algorithm. The idea behind the algorithm is to combine the observation, the historical observation, with the climate model predicted future data in order to update and produce the IDFs for the future conditions. So we have on one side, historically, the two relationships are being used. One is the relation between the historically observed sub-daily data and historically observed daily information. After extraction of the yearly maximums and fitting the GEV and application of the quantile mapping algorithm, the relationship can be developed. And this relationship is combined with the second one, which links the daily historical data to future daily data produced by different climate models and emission scenarios. Again, with extraction of the yearly maximums, fitting the GEV distribution and applying the quantile mapping algorithm, we were able to combine these two relationships and generate IDF curves for the future. So that's the main kind of idea. The graphical representation is here. So the first relationship is sub-daily observed to daily observed. And then the second relationship is daily observed to daily future predicted. And these two are combined in kind of updating and producing the IDF curves for different durations for future conditions. This is just a kind of mathematical representation of that quantile matching, what I kind of try to describe in words. And the second main contribution, the second main part of the tool is related to ungauged location. This part of the tool required a totally different approach. And what we have done is we utilize the kind of reanalysis data for the period between 1979 and 2013 that covers the whole country in a grid format, and 31 variables from the two reanalysis products, the North American and European, and then select this kind of atmospheric variables for each location, so each grid location, and development of or use of the support vector machine learning algorithm, which is nothing else than sophisticated correlation type of analysis to define the relationships between the sub-daily annual maximum precipitation series and predictor variables that are selected. That is then kind of combined, and the calibrated model is calibrated support vector machine learning algorithm is developed for each location, each grid point. And what we have done, then we introduce the kind of check or the correction so that the grid predicted values are then corrected spatially by taking into consideration the closest observation gauging stations. So we did the updating or correction with taking the 10 closest and 25 closest stations. So that basically produced the grid information for maps with IDF curves for each grid point corresponding to two reanalysis products and two sets of corrections, 10 and 25 stations, taking 10 and 25 stations. This is the list. I'm not going to go into details. A list of these 31 atmospheric variables that are used as predictors. This is the kind of illustration I'm just showing to year 5 mean precipitation. This is the European reanalysis. This is North American reanalysis. Different shades are showing the precipitation. And the maps at the bottom are showing just the same kind of information, but applied with application of the correction utilizing the 10 and 25 stations. How is this then? This was the input. This was the kind of historical IDF information for all the grids covering the country. And then the kind of quantum matching algorithm required some modification. So we use this gridded estimation for representing historical IDFs for sub-daily with the daily, combined with the daily to get the first relationship. Then we use the daily and daily historical and daily future to again get the second relationship. And then we combine these two to kind of generate the IDF curves for the future. So now in this case, the user basically can click and select any location. Each location will belong to a particular grid cell. The system will identify the kind of grid cell and be able to produce the IDFs for that particular location, produce the kind of historical from the input maps and modify under different climate change conditions for the future. That's the basically mathematical relationship that is describing the quantum matching algorithm. Okay, so this is a really fast walk through the methodological background of the tool. Let me now just walk you through the implementation part, and then the rest of the stuff you can either inform yourself from the provided slides or publications, or simply through the questions and answers. The tool is developed in a traditional form of the decision-based system where you combine the user interface with the database and the model base. So the user interface is used to manipulate data, present the results, tables, equations, graphs, and so on. The database is the main depository of all the historical data as well as all the climate model data for now the 78 models that I indicated we have the data for. For the CMI 6th, we have 4 SSP scenarios information. For the global climate models for the R5 or RCPs, we have 3 emission scenarios considered. And also we have, because the climate centers are providing multiple runs of the different climate models with the different emission scenarios. So we are storing and using all these different runs. So very large number of future climate conditions or climate model outputs is covered by the database and the tool. And as I pointed out, in addition to these global models, we have a 24 peaking bias-corrected GCMs. We also have the ungauged IDF data set that's for the whole Canada landmass. These are the kind of input maps that I indicated, a couple of slides back. The model base includes basically statistical algorithms, Gumball GEV, the equidistant quantum matching algorithm for both gauged and ungauged conditions, and some optimization models that we use basically to fit the equations and to the data. Here are some of the kind of details of the process so that you can understand what's going on when you go through the system. The user starts by selecting, option of checking or updating the curves for gauge location or ungauged locations. If you take the path through the gauge locations, the interface provides the location of all the 700 stations with all their data. The IDs and everything else. So through the kind of interface, the user is able to select the location, and automatically by selecting the location, upload the necessary or available historical observed information. When there are two options on the menu. One is development, as I pointed out, historical IDFs, basically replicating what Environment Canada is publishing. And the other option is developing IDF curves for the climate change conditions. In the case of the historical one, the historical information for the selected location is being kind of entered into the tool from the database, organized in the form that the data is checked, ignoring negative zero values, extracting the yearly maximum, and then the Gumbel distribution is fitted in the case of historical to the data to provide for calculation of the IDFs, and then we fit the equations using the optimization algorithm, as well as the kind of prepare the data for the display in the tabular form, in the form of the plots. This is what you see on the left-hand side, and the equations. For the future IDFs, option for the future IDFs activates a number of steps that require input for the future or development of the future IDFs. So the first is the selection of the GCM model. There are options to select individual models. There are options to select the ensemble. There are options to kind of do various combinations of the models, depending on the user's interest. Again, after the selection of the model, extraction of the data series is being done, organization of the extremes, and then application of the quantile matching algorithm, calculation of the distribution parameters, and then generation of the IDF curves for the, okay, I'm sorry, I think I mixed the, yeah, I'm sorry. There is a smaller problem with this. There is a small problem with the slide. So, for the selected models, for the selected emission scenarios, the kind of data is being extracted. The GEV is fitted. The algorithm, the quantile matching algorithm, is applied, and then the IDFs are calculated. They're calculated and presented in different formats. This text corresponds to ungauged locations. Yes, I do have that here, and I thought that we are talking about. Okay, I'm sorry, it's my fault. So for the ungauged locations, we go through the process in a relatively similar way, except the beginning, where the user interface offers basically a map of Canada. The user can kind of click and select the location. By selecting the location, the data is being uploaded from the grid database that's stored within the tool. And then development of the historical one is basically reading the information, calculating the IDFs, and finding the average curve. The reason why we introduced this is that we do have two reanalysis products, and we have two different two different correction schemes. So there are 4 products at the end, and instead of confusing user with the 4 of them, we are simply aggregating these 4 and finding the average one that's presented to the user as a single IDF relationship for that particular location. And again, the data is being displayed and organized in a very much the same way as for the gauge locations. For the ungauged locations, the process is relatively similar. This is what, I kind of created the confusion. I hope you will understand. We are extracting again for the particular location. That's in this case the grid cell. For this grid point, we extract the historical data from the input maps that are kind of stored, and then go through the application of quantile matching by extracting fitting distribution and applying the modified quantile matching algorithm to come up again with 4 different IDF curves. And these IDF curves are then averaged to kind of give the final or the single IDF curve for the selected location. Here you have a location, for example, 1 point, and for that point you get the curves, tables, plots, equations, and uncertainty range. So this is the way of kind of implementing. You can update historical curves, which are published by the Environment Canada, selecting station, applying the procedure, and generating the curve. We also have opportunity to generate the future curves by then implementing the quantile matching algorithm. Beside the gauge locations that are covered by Environment Canada, the tool allows individual or input of stations or data that users may provide. So in that particular part, the user creates the station, identifies the location, provides the data, and then when the data is in the tool, apply the basically same procedures for either generating historical or future IDFs. For ungauged locations, we have a relatively straightforward process of selecting locations and then obtaining either historical or future IDFs. Detailed technical information is available in the technical manual. Both of them, and user's manual actually walks the user through the process of developing different gauged, ungauged, user created station, and so on. So all the different ways of using the tool are incorporated in the user's manual. Both of the documents are available through the tool directly, or at the websites of my research group or my personal website. In addition to the technical documentation, we also try to publish and get the kind of confirmation of the peers that the methodology and the work that's incorporated into the tool matches the current kind of research environment. So there are a number of papers that are available. They're all available through the tool that are documenting the development, the methodology, of the gauged, ungauged, the quantum matching algorithm paper, and so on. We have a regional analysis data and 2 papers that are dealing with a kind of some testing of the regional climate models versus the global climate models, as well as using some kind of spatial interpolation to possibly generate the data for ungauged locations. And that was done before basically ungauged component was added to the tool. We have also the engagement practice paper that documents the survey that we did with the users of the tool, as well as documenting the procedure of the public engagement in the development of the tool. So I pointed out that you can, through the tool, obtain almost all these different publications and manuals. Also on my website, you can find additional resources, presentations, some PowerPoint presentations, some YouTube videos that may be helping those who may have interest to pursue this further. I'm going to stop here. I think I used my time, and I pointed out that you do have in the presentations 2 more sections that may be of some value for those who may want to go a little bit deeper into this. Thank you very much. I will be very happy to respond to some questions.
So thank you, Professor Simonovich, for your presentation, and we got a couple of questions. So one is the first question, do you have any thoughts about extending this work beyond 1 day duration and 100-year return period?
The tool is actually providing the IDF curves from 5 minutes to days. So that's all. This is what I call the sub-daily information. So 5, 15, 30 minutes, and hourly data is, or IDFs are produced. However, the return period we are only covering until up to 100 years return period. We're not planning to look into different return periods. I must tell you, we didn't get very often requests like this. If this is something of the interest of the community, there is the possibility to think about that.
Okay, the second part of the question was like, what about PMP, probable maximum precipitation?
What about?
Well, I guess the question is, do you have any thoughts on how you would adapt probable maximum precipitation? This is coming from dam design, which is usually a much higher period designs, and so it keeps coming up. I'll be talking about it in my presentation later a little bit. Yeah, these much higher return periods, and how do you deal with that? If you have any thoughts, maybe not just.
Right now, as you can see, the methodology is very much kind of following a very traditional way of developing the IDF relationships. They are, we kind of started from that point that, most of the municipalities are using the IDFs in everyday work. They are using them they're being provided from Environment Canada, and that's where we kind of started building on by bringing the climate change into that and so on. We didn't think about, other potential users. I cannot directly answer, for example, how can you bring the probable maximum precipitation. We do need the kind of time series of precipitation. Right now, this time series is annual maximums. If you generate any other way, this kind of series, it may go there into the tool and basically into the methodology. I really need to think a little bit more serious about the ways how that may modify or require modification of the algorithm, especially the quantile matching. Yeah.
Okay, so thank you. We got a second question. How does the system handle gap fillings for station observation, like the observed stations? So how the system deals with the gap filling?
What we have done is we're limiting the use or the length of or required length of the observations. In the case, so to 10 years, and that's a really open question for the discussion among the hydrologists, and I'm sure. But for the missing data, we did develop the tools which are in that. When I was explaining the steps, I had one step which was kind of check of the input precipitation series, and one of the steps and check is also the interpolation for the cases where that that may be required. So we do have some, this is not an extremely sophisticated way of, interpolating the information. It's just using the data that are available and kind of, doing the relatively simple. But that's kind of covered, I would say in the data. If the very large portion of the series is missing and basically compromising the value of the whole inflow sequence, precipitation sequence, that cannot be obviously that station or cannot be used or extended or updated for the future.
Okay, thank you. So the third question is, let's say if we run that tool now, so would it take the historical data up to today, or it would stop to a certain time?
No, the historical data are the data that Environment Canada is providing, and as I pointed out in the version 5 that we just posted in July, the historical precipitation information is provided up to 2017, and that's what we have. If the users have their own data, they can very easily create the station and then kind of combine the Environment Canada data that's available to 2017 with the user's data, let's say updating this to, today. So that will be like a user created station that combines two pieces of information together. But officially, the tool and Environment Canada is providing data up to 2017. The moment when the Environment Canada updates and provides the new precipitation data, we update the database.
I think that's very useful information. The next question is kind of a comments and the question. So thank you for showing that. I really appreciate how directly applicable this work is for practicing engineers. I often encounter hydrology research where it is difficult to understand how to translate this to a real engineering practice. So can you provide advice for how to approach research practitioner partnership that result in tools or conclusions that are useful for both sides? So it's
that's a good question. That's a good question, and I think it's a little bit beyond the IDFs and this work. It's a question, how to bring the research into practice, and most of the research is developed either at academia, university labs, or government labs, and kind of work with the practitioners is not. At that stage is not the priority. We were really, in this particular case, we were lucky. We were lucky that basically, Canadian Water Network particularly targeted that link and application of the knowledge. Knowledge application was the kind of keyword in that particular call. That's not happening very often. I've been in academia for a very long time. The best we were able to do, and that's, I think, the privilege of the engineering faculties, is to go through some kind of collaborative projects where the research component is funded by the NSERC and the government type of funding, and the practitioners participate with some portion of that. Again, having a number of these collaborative projects, I must tell you, is kind of mixed experience. The people in practice are not available all the time. some companies are very hard approving the time for investing the time in the kind of development of something that may be of value later, because they do need resources, people, and time of the people and experts on a daily projects. And it's a tough question. I think in this case we were in a very good situation. Also, I think the very strong support and interest of the municipalities that we were talking to was essential. They were pointing out, we do not have that expertise, and we need something like that. So that really helped, and I can tell you that I am tremendously thankful for the participants from the Toronto and Hamilton. These were the people who were on a weekly basis with us, almost reviewing every step of the development of the methodology, implementation of the methodology, and testing of the tool.
Okay, so thank you. The next question, I think you probably answered partly of that, but what the historical data sets from ECCC only, or also any other climate station data, like from any provinces or any municipalities?
The database, our database, the tool database, contains only Environment Canada data. But we have as I pointed out, the tool can accept the other data, can accept the stations as well as the observations and the information that some other sources are providing. That's a very simple process. It has two steps before basically what I was showing as a procedure. And the steps are identification of the location and input of the data, and input in the form of the time series of annual maximums, and then goes into the same algorithm and can develop the IDF curves for these different locations. We also did build with this particular task of creating station, that if Khalid creates a station, that station will not be available or visible to me. But Khalid can select a group of users. So like you may have like Alberta observing or collecting information on some stations in addition to Environment Canada, and you can mobilize all the people in Alberta and allow them to actually see the tool with this, separately created stations. So that's a kind of nice for the situations that, let's say, you are covering a particular region, and in the region you collect the information of the multiple locations. You can kind of bring all that into the tool as a user-provided stations, and then encourage or identify who are the users of that part of the tool.
No, thank you, Professor, and I think that's a very wonderful option to have. With that, I think we are out of time, and we have one more question, but probably I'll pass it to you later so that you can answer, because we are running probably 1 or 2 minutes behind. Thank you, Professor.
Thank you. Thank you.
Yeah, thank you. On behalf of all the community of practice and all the people attending today, thank you, Dr. Sminovich, for that information. It was really interesting and useful, as was mentioned in one of the questions. So thanks for joining us. And of course, you are welcome to stay for the rest of the conference if you like, and listen in by all means. Or if you have to go, we understand.
Okay,
Thank you so much.
Thanks very much.
Okay, next speaker actually kind of dovetails or continues the discussion on intensity, duration, frequency curves. Ernst Kirkhoven with the Alberta Energy Regulator is also going to present his thoughts on applying climate change to IDF curves. Ernst.
Okay.
Are you muted?
Unmute.
Oh.
No. I just
Okay.
I struggled to unmute because I didn't want to.
Okay.
Okay. Hello. This is going to be a very unbranded presentation, and I'll give a caveat on this in a moment. So I just want to say, for especially this is being recorded, the following presentation reflects the personal professional opinion of the presenter. None of the contents reflects any operational or regulatory policy decision on the part of any provincial government body or agency, just in case this gets out there. And so I'm only presenting this with just to initiate continued discussion on an emerging issue that I think we need to talk about in the community practice and take advantage of some external people who might be on. So this particular presentation is in some way triggered by something that is in the relatively recent 2019 Alberta Dam and Canal Safety Directive. So particularly 5.51D, which says that dam and canal designs are required to use the best available practices in hydrologic and hydraulic science to be applied to estimate the inflow design flood. So the question that comes up is, okay, does best available practice in hydrology mean that you have to include extreme rainfall due to climate change? And if so, how would you do that? And so Dr. Simonovich gave us an example, but I know also this is the closest thing we have, I believe, in our policy directive in the province. What I'm finding increasingly in my work is that the general issue of how do we include climate change into extreme designs is coming up in EIAs, project hearings, APIA renewals, and things like this, from statements of concern, from NGOs, sometimes First Nations consultants, things like that. And we don't have a great answer for that right now. So there's two general approaches. The last presentation gave an example of what's basically the modeling approach, which I will very simply summarize as basically modeling the future scenario, get the IDF stats for it, model the past, take the difference, add it to the observed, and you get a new IDF. And the other method that is showing up a lot in the literature is something called a temperature scaling approach, where the idea is you apply a percent change to the extreme precipitation per degree of mean global temperature change. And that percent change would be a local parameter. So most of my discussion will be about the temperature scaling approach because I was anticipating Dr. Simonovich would give a lot of stuff about the modeling approach. So I'd given an earlier draft presentation where I talked about the UWO tool. You've already seen this. This is a slightly older version, but same idea. But the other thing I wanted to point out was that we have the Quebec Code Pluvial recommendation, where, as far as I'm aware, it's the only approved regulatory approach to dealing with this in Canada, and was a result of a synthesis of regional and national modeling studies, and mostly based on, although it was more than just that, two in particular regional studies from 2011 to 2012 that were, here they are, a brief summary of them. They're very similar in concept. They were regionally averaged modeling studies published in various journals, looking at extreme 24-hour, 100-year, 2 to 24 type rainfalls, and then grouping them by ecoregions. And when you look at those ecoregion results in Alberta, you see that they're predicting numbers of 10 to 15%. And in Quebec, it's maybe a little higher. And I bring up Quebec because this went into the recommendation, how they got there. And then Melo, the same Melo who was from one of the studies, was commissioned to write a report for Quebec in 2014. And he recommended, or his group anyway, recommended a regional distribution between 18 and 20% across the province of Quebec based on those studies. And then Quebec took that and said, well, we're just going to call it 18% in their Code Pluvial. So this is all French, but it's their document from the Ministry of Environment. And basically saying that when you analyze, you have to increase it by an extra 18% to take into account climate change, at least, if I read this right. My technical French is not great, but I think that's what it says. And as I said, I think my aware that's the only thing we have out there in Canada in terms of something with some teeth. Interesting that came up in one of our hearings. This is all public record stuff. At the Benga Mine hearing, Benga had used at one point this UWO tool, slightly older version, probably the version 4, to estimate the climate change question for its preliminary designs. And there was a comment from the ECCC. This is what they said. It's rather technically verbose, but to paraphrase it, my interpretation of it is basically saying is that these people weren't necessarily great fans of the modeling approach, not because it's wrong, but basically they're saying individual model runs are too short to reliably capture the statistics of extreme rainfall. And therefore, this sort of approach can potentially add a lot of noise into the method, especially for rare events. And so they felt, and they quoted this Lee article, I'll get back to that, that these methods are unlikely to capture the local extreme precipitation response because of just too much uncertainty. So they gave an example in the Lee paper, where these are two model runs using the same model but slightly different running conditions, initial conditions probably. And what they were pointing out is that these two different runs, there's 35 in total, but they took the two extremes to show for the presentation, is that there's very little, virtually no structural similarity between the two. And the other point is that there's a lot of, it's very bumpy, basically, is that there's a lot of, if red means low and blue means high, you have adjacent dark reds and dark blues, because it's, my interpretation is just whether or not in their simulation a storm happened to pass through there or more than one. Well, another area right beside it didn't. So what does that mean? So this recommendation, as I said, it's coming out from ECC in response to companies that use the UWO approach, is that it's unlikely to produce robust projections. So there's concerns that it's not reliable in terms of the again, the noise aspect. So what they particularly recommended was using the 2019 Canadian Standards Association guidance, which had a simple scaling technique to adjust precipitation as percentage of projected temperature change. And so this is the reference document they were talking about, which unfortunately is only available for purchase. I have not personally been able to see a copy of it. This description is, and I can see the table of contents, but if anybody can help me find this, that's great. But there are other temperature scaling approach work that's been done in the literature. So I'll summarize that. So what is a temperature scaling approach? It's basically at its fundamental level based on the concept of the saturation vapor pressure equation, or Clausius-Clapeyron equation, sometimes called, and others names for it too. But I'm sure we've all seen this in our hydrology undergrad, vapor pressure in pascals as a function of temperature. And this equation is almost exponential, not quite, because T is in this new denominator here, but generally it means that if saturation vapor pressure increases at 6 to 7% per degree Celsius, depending on the temperature. And this is usually the starting point when you quite often hear talk about what effect warming will have on extreme precipitation, at least at a global large scales. And that we'll get more to later, but globally, a lot of the GCM results we're seeing are showing that at a global scale, precipitation is, in fact, doesn't seem, when they model them, it doesn't indeed increase at roughly 6 to 7% per degree of warming. So here's another paper from 2020 in Nature by Tabari talking about this concept. So as I said, I'm reiterating, extreme precipitation is expected to intensify at a rate about 6 to 7% per degree temperature, but there's the atmospheric dynamics, which can weaken or reinforce this effect regionally to modify the amplification, and that also water availability also plays a large role. So it makes a difference whether or not you're in the middle of the continent or on the coast, for example. So Tabari, in their study, comparing the late 20th and the late 21st centuries, and they broke the world up into 4 regions, one of which was the semi-humid region, and this is a zoom in on North America, that's why it's a bit blurry, where Alberta primarily is. So Alberta is roughly here. This is Lake Athabasca. And under his results, he was finding that if Alberta is mostly this blue, that's the 4 to 6% change per degree Celsius for Alberta. And I'll reiterate that the temperature scaling that you're talking about in these studies are usually expressed in terms of global mean temperature change, not local temperature change or summer change or anything like that. And the idea is that they want to reflect the fact that these are due to much larger scale circulation patterns, not just local temperature effects as well. So they tend to when they express these indices, they're with respect to global mean temperature change. So Tabari looked at 4 regions: humid, semi-arid, and arid. And this is a scatter weird little plot for the 30-year event, 24-hour. So for the semi-humid in Alberta, they found the average was just under 6% per degree Celsius. You had similar ranges across the type, so there was more variability in the drier than the wetter. And the other thing that they found was that for more common return periods, there was a bigger difference between the dry and the wet regions, but at higher return periods, they are sort of getting closer together and approaching that 6 to 7% range. And this is for engineering design, we're more interested in this than we're not really usually so concerned about 2 to 5 year events. So back to the Lee, what they did is they took 35 model simulations from a single model. So this is, I'm just changing the initial conditions slightly and then letting them run. And they found that when they averaged them out, that for the 2-year event in the area of Alberta, they're looking at 2 to 4% per degree Celsius. And then at the 100-year level, 6 to 8%. And in this chart, the slashes mean that it's consistent, that rate is consistent with the Clausius-Clapeyron equation. So they're basically finding that extreme events start to approach the 6 to 7% you get from the vapor pressure curve. And at lower return periods, it's, well, you know, they get close to that in the coasts, but not in the center. And as you get to more extreme, it's only the very center of the continent that's isolated enough not to get that scale. So we also just had the release of the 6th assessment report this past few weeks. So recent that when I try to pull figures out of this, they still have the accepted version for final editing watermarks in them. So please try to ignore that, but these are not final anymore. I mean, these are not, these are final. And so they've had a number of results that they express. So this chart here showing the relationship between global warming in degrees Celsius above 1850 to 1900 and percent increase intensity for 10-year events and 50-year events. And as you can see, they both follow more or less in lockstep, roughly 7 degrees per degree Celsius. Then when you look at the regional distribution across 3 different temperature warming scenarios, you consistently see that Central North America, the Alberta area is lower than the rest of the world, on average at least. They tend to be the lighter colors of green rather than the darker. And if you zoom in on North America for the 4-degree warming, you'll find that Alberta is in this 10 to 20% range change for 4 degrees warming. So that's implying something like 2.5 to 5% per degree Celsius for an annual maximum daily precipitation event. So that's a 2-year event. And they give another sample based on the same sort of information, but now they're breaking it up by total change, the thermodynamic component, and then the dynamic component. So the thermodynamic component is fairly uniform globally with a little bit of increase at the poles, probably because it's warming it more at the poles. And then you have a, relatively speaking, the middle of continents of drier dynamic effect. And when you zoom in on North America, you get about, that's the color range for 3 to 6%. Per degree Celsius. So a lot of things pointing in the same direction. Last thing I'll point out on this particular part is you also have trend analysis you can do on stations, and I just want to make sure you're aware that you do that very carefully, because anything you do with this, there's a lot of variability, and so an individual station, you're unlikely to get a good temperature, a good trend, even if one might actually be physically existing. So in the same report, sorry, they have, oh, sorry, just a moment. In this report, they have 8,345 stations with sufficient data to do a trend analysis. Significantly more had positive trends than negative trends. And then the ones that had significant trends were far more likely than negative trends. So, but still, the vast majority were non-significant, probably mostly because of the variability. Nevertheless, overall, there's far more evidence of increasing extreme precipitation across the whole world, including North America, than there is of a drying trend or a stable trend. Although an individual station might be too noisy to detect that. So that gives you an idea about the scaling percentage, but then it still leaves you with how much delta T are we talking about? And that's dependent on what time frame you're looking at and what emission scenarios you're looking at. And again, this is from the IPCC. These are the 5 main scenarios you see. I believe that the work we just saw were the UWO has these 4. But these are the 5 that get presented a fair amount. So just to give you an idea of where they are, this 1.91 is a very aggressive mitigation scenario where you're looking at being net zero by 2050 and then going negative in carbon intensity emissions. 2.6 is roughly the sort of the Paris Agreement type scenario. Then you have these, what I'm calling serious half measures approach and a stabilized growth where you stop being exponential, more linear growth out of emissions globally. And then you have the most extreme scenario, the 8.5, which I'm tongue-in-cheek calling coal burning cars scenario, where this is a very coal intense scenario. This is the extreme scenario. We'll get to what those look like a bit to give you an idea about how different they are. So anyway, in the near term, they're all pretty much the same, and then they progressively diverge as you go towards the end of the 21st century, depending on how emissions growth goes. And so the question of, which one of those do you choose? And this is a plot of the emission pathways in terms of annual emissions of carbon equivalent. Ask you to focus on the before 2100, because the study I was pulled this from was trying to look at beyond 2100, but most scenarios you're looking at are focused on the 2000 to 2100 range. And so you see the various pathways. The extreme pathway peaks late century. And I think here they start to run out of coal. It's so intense, so extreme. And then these other scenarios, I circled the 5 that are in the chart. And then the most strongest one is this sort of greenish one where they go to net zero and then they go negative. This is the most optimistic. 2.6, as I said, is the pathway that Paris Accord, something like that, is supposed to achieve. And this is the same chart, but looking at CO2 concentrations rather than emissions, so how that would develop over time to 2100 and then beyond. And you see there's a large range of difference between these, and that has a lot of consequences for what that might mean, especially if you go beyond 2100, but we won't be discussing that too much, but you should keep this in mind of what sort of these scenarios look like in the very long term if you're interested in long-term infrastructure. This is a little scary, but we could, in theory, be on any of these pathways. So to put that in some immediate historical context, this is a plot of the annual NASA GISS temperatures for the Earth mean average anomaly, where that means it's been normalized to have a 0 value on average between 1951 and 1980, so in here. And what you can see is that there was some slow, noisy increase. There's reasons for this, but ever since 1970s, we've been in an era for the last 50 years or so of roughly steady, maybe rather stable, 0.02 degrees Celsius per year, or roughly 2 degrees per century temperature growth that has led us to being now roughly, as of this year, it's right on, and this is a smoothing line, but roughly 1 degree warmer than the 50 to 80 baseline globally. And these are some time shot snap averages. The one I want to focus on is 1971 to 2000. Because that's where a lot of our hydrology data is coming from, where IDF curves are derived from temperatures from that era. And I just want to point out that that era is almost half a degree warmer than the 1800s. And it's also almost 0.8 degrees cooler than today. So if you consider that with a 6% per degree Celsius, this implies that the 70s to 2000 data is as a whole may be on the order of 5% low by current standards, or that we're 5% higher now than what was going on back then, on average at least. So just something to keep in mind. That might not be considered a big deal yet, but it's growing. And so projected change in temperatures relative to the baseline going forward, so readjusted, because I want to focus on where most of our data is coming from. And if you look at those medium to high scenarios, the 4.5 and the 7, but not the crazy carbon one at 8.5, and just look at what kind of temperature changes they're predicting, you're looking at 1.1 degree warmer over the next 20 years than 70 to 2000, an extra half degree by the mid-century, an extra degree and a half roughly by the end of the century. This sort of increase is equivalent to a 0.275 degrees Celsius per decade temperature increase going forward. And again, with a 6%, if you take that as your scaling parameter, that translates to roughly 1.65% per decade, or to keep the numbers simple, roughly 5% for every 30 years going forward. So to summarize, I'm my way ahead of schedule, but direct modeling techniques can have a high uncertainty due to small sample size, not necessarily a critique of the UWO work from me, but it is out there in terms of ECCC has been saying this to us. And from their point of view, temperature scaling techniques are less sensitive to this. Be aware that Quebec has implemented an 18% increase in IDF values for its code. If you apply similar approaches and look comparing Alberta to Quebec, you would find that generally Alberta's expect to have a less percent increase than Quebec or the global or the Clapeyron equation would suggest, but not by a lot. It's sort of a scatter, but almost every study ends up between 3 to 8% increase per degree Celsius. And so if you take a number like 6, a sort of middle, but not too middle, not too low, but a little bit above middle, this implies potentially a 5% change in IDFs since our historical data. So what I want to emphasize there is you have a data station with a whole lot of data. You're great, we've got 50 years of data, we can get a better estimate, but then it's old. So it's a trade-off there. And then looking forward, we could be looking at an additional 5% per 30 years going forward as a sort of like a rule of thumb to keep a guide for what's a reasonable number when you see it. And some concluding remarks to elaborate on that a little bit. I just want to make sure extreme rainfall in Alberta is far more likely to increase than to decrease or stay stable. So there's a slow trend that we're on, and I would put it at roughly 5% per 30 years of our standard engineering stationarity assumptions are going to push us to under design of water management infrastructure. So it might be okay for now, but where's that line? It's a bit fuzzy. And as I said, that for Alberta, that the older data might, the pre-2000, last 70 to 2000 might already be roughly 5% low, and that we can expect about 1.7% per decade going forward. You can put a range on that. I would put it between 1 and 2.5. So anything less than 1 is probably unlikely, and anything more than 2.5 is probably unlikely, but anything in that range is well supported by a broad range of evidence. My concern here is, which I noticed a little difference from the way Dr. Simonovich talked about the reason for his reason was municipalities wanting to have this information. But I'm finding from the regulatory side of things is the applicants don't want to put this in, and so how do you get them? And there is one of my concerns is that there's a large body of literature out there. You can use a lot of GCMs, use a lot of scenarios. It's relatively easy, I believe, that for an applicant or a consultant to pick a peer review literature and say, this is the one we're going to use. It's hard to attack them for that. At the same time, you just don't know if they're cherry picking it. So the backbone I'm looking for, it's some backstop here of are there some sort of basic approaches that we can look to some minimum standards, something along the lines of something like the Quebec, it doesn't have to be exactly that. And what I do expect is that we can expect to see each year, decade going forward, increasing pressure to provide public guidance on acceptable methodologies on this front, or some rough guidance, doesn't have to be specific, use this approach, but something. And there's also going to be an increasing need for consistent decisions on how we interpret this going forward between different regulatory bodies, different projects, and therefore a need for more internal and external discussion on this issue. So that is a blast through. I guess I used almost my whole time. Sorry. Any questions?
Yeah, I don't. So last year, I remember I was able to put a little time check on the screen, but I don't think Teams has that. But yeah, we might have time for one very quick question or observation, but yeah, we're running a couple minutes right now over. So
yeah, so Michael, I think Professor Simonovich commented on like a temperature scaling. So I think it's better if he just speak.
I'll say very quickly on that is, yeah, I ran into this, is that there seems to be two camps out there, and they each think theirs is better than the other, and it's very hard to argue between them as a middle. So yeah, I expected that. Yeah, there seems to be a temperature scaling camp that doesn't like the models, and that there's some evidence from the models saying that they're better. So yeah, that's one of the other things I'm worried about is this. It's hard to split that hair. Oh, I won't call it hair. Split that issue as a regulatory person.
Well, Dr. Simonovich did put a link in the chat, so we could definitely, that would be something that we could follow up on. And I see there is another question, but we'll have to take that offline and have it answered later. Thanks so much, Ernst, though, as usual, pointing to more work for the community of practice to sort of think about, and probably sooner rather than later. Okay, I would like to move on just so we can respect the timeline for ending with a break, and also to give Brandy her time to present her work. Brandy Newton with Environment and Parks is going to talk to us about future shifts in winter temperatures and the precipitation patterns in Alberta ecozones. Brandy, are you all ready there?
I think so. Thank you.
Awesome.
Just trying to get it uploaded so that it's presenting. Okay, can you see my screen okay?
Yeah, that's good.
Fantastic. Okay, thank you. So the research that I'm presenting today is actually just a small part of a larger study that we did that was published earlier this year. And so I'm just looking at one of the future scenarios. Basically, motivation for this work came from the importance of the snow accumulation and melt for water resource distribution, so particularly in the mountain headwaters, which supply the majority of our water on major rivers in Alberta, where snowmelt is the major hydrologic event on these snowmelt-dominated rivers. The freshwater is critical, of course, for just a variety of socioeconomic and aquatic ecosystem and terrestrial and hydrologic functions. Our snow accumulation and melt are, of course, very strongly influenced by air temperatures, precipitation. The phase of precipitation dictates whether or not it's falling as snow or as rain. And the temperatures fluctuating above and below 0 degrees affect the snowpack. And when we start seeing temperatures that are above 0 degrees, we increase the likelihood of rain or rain on snow if there's already snow on the ground. So I wanted to take a look at different ecozones. So looking across the entire province, there's considerable climate gradients in Alberta with elevation and with latitude. And so I looked at the entire province, but then also looked at what the averages for different ecozones are. And we can see in this table that there are considerable climate gradients. Our prairie, parkland, and boreal zones have agriculture. We have some sporadic discontinuous permafrost in northern Alberta, as well as poor drainage. Mountains are the steep rocky terrain, and foothills are that transition between the mountains and the plains, the forest and the grassland. Interestingly, the foothills contain several dams and reservoirs, so that makes the foothills a very important region for water management. For this study, we used high-resolution downscale daily temperature and precipitation projections for the 2050s and the 2080s. And for the full study, we evaluated a historic period, the 2050s and 2080s, using RCP 8.5 and 4.5. In this presentation, I'm only going to be presenting the results for 8.5. I can provide details on how the GCMs were selected if requested. It's also in the paper. For temperature metrics, we're focused on two temperature metrics, the first being the spring 0 degree isotherm. So this is the date in which the mean daily temperatures shift from below to above freezing. And winter duration which is that period between the autumn and the spring 0-degree isotherm. So to smooth these temperatures, we used a 31-day running mean, which smoothed out some of those daily fluctuations over sort of several weeks to a month. For temperatures as well as the precipitation metrics, we were evaluating the future scenarios relative to a historic baseline period of 1950 to 2017. And the reason I'm using this large, lengthy baseline period is the paper, the full study used that historic period for historic trend analysis as well. So we're looking at the changes in the mean and the 10th and 90th percentiles, where the 10th and 90th percentiles represent the extreme low and high ends of the climatologies for these future periods. And looking at these because, of course, we know that mean values don't occur every year. For precipitation metrics, we looked at total precipitation from November to April, as well as total snowfall over this period. So the snowfall was defined using a temperature index precipitation phase algorithm, and precipitation that fell on days where the mean daily temperature is below 1 degree Celsius was counted as snow. And because we wanted to look at the covariability between precipitation and temperature, the total precipitation is given as a cumulative distribution relative to mean daily temperature, which you'll see when I present the results. And we also calculated the probability density functions for total precipitation and snowfall, which is how we're showing the variability in the climatologies in the future scenarios. So starting with the temperature metrics for results, these are the results for the timing of the spring 0-degree isotherm. So the top row in this figure is the 2050s and the bottom row is the 2080s. And this is of course, the RCP 8.5 scenario. The values that are given in the scale are departures from the historic baseline period. So the departures from 1950 to 2017 mean 10th percentile, 90th percentile. So the 10th percentile represents those spring 0-degree isotherm dates, or the onset of spring, that are extremely early, where the 90th percentile would show those spring onset dates that are extremely late within those distributions. So what stands out here is the mountains and somewhat the foothills and part of the prairies as regions that are projected to have higher rates of change compared to the other ecozones in the province. So similar maps, but for winter duration. These again show the top row as the 2050s and the bottom row is the 2080s. Once again, we see the mountains stand out as a zone projected to have some of the largest decreases in winter duration. In particular, if we look at the 10th percentile, we see some rather large departures from the historic baseline period, particularly for the 2080s in southern Alberta. So I summarized this a bit in a table which shows the ecozone averages. So this top row shows the change in mean. So for example, the mean winter duration over the mountains, the historic period was 187 days. And this is projected to decrease by 44 days in the 2050s and 69 days in the 2080s. What stands out is that we have uneven rates of change among the ecozones, which we saw in the maps. And this is going to change the climate gradients that we presently see across the province. So where, historically the mountains had the longest duration of winter, in future scenarios, the mountains may have a winter duration that is shorter than other ecozones in the province. Something else that really stands out in this table is the changes and in the corresponding maps is the changes in the 10th percentile, which is the extremely short winter duration in the distribution climatologies. So for the mountains, as an example, if we look at that 10th percentile in the historic period, kind of that extremely short winter duration would be about 168 days or less. And this is projected to decrease by 58 days in 2050s or 88 days in the 2080s, which actually gives us a winter duration as short as 80 days in the mountains, which is just ludicrous. And then similar for the prairies, we see these very large rates of change under the 10th percentile, so that extreme end of the distribution, where in future scenarios in the 2080s, we could have winter duration that is approximately 1 month. So what appeared in the results when I was looking through the results is that these were ecozone averages, but there were regions within each ecozone that were projected to remain above freezing. There was no autumn or spring 0-degree isotherm were detected for a certain number of years, and in particular for the 2080s. So just picking out some of the major cities in Alberta and plotting what the percentage of winters that are projected to remain above freezing. We see, like, for example, Calgary, 6% of that 30-year climatology in the 2080s is projected to remain above freezing. And there's a fair bit of variability in each of these ecozones. So moving on to precipitation. So we were interested in evaluating the covariability of precipitation and temperature. So rather than showing precipitation as a sum and mapping it, or showing it as a time series, what we did was calculated the sum of daily precipitation for corresponding temperature bins. So the temperature bins, if the daily temperature was -10, we summed all of the days that were -10, how much precipitation fell on those days. And the advantage of this is that it shows us the amount of precipitation that falls below a certain temperature. And in these graphs, I'm showing that 1 degree threshold that we used to separate the rain from the snow in our calculations. And but we can use this to evaluate any temperatures. The caveat to this is that it's not showing a time series, so it is not necessarily representative of a snowpack, because for some regions, for example, the prairie, it is not uncommon even at present to have snowfall and then melt, and then snowfall and melt throughout the winter. So this is really just showing the amount of precipitation that is falling at certain temperatures between November and April. So we can see using these cumulative graphs is how much of the projected changes in precipitation are expected to fall as rain, or is expected to fall as snow. And so just on the bottom right as an example, where the green shows that historic period from 1950 to 2017, and then we've got orange is the 2050s and the purple is the 2080s. Looking at the 2080s, we've got a portion of the increase in precipitation that is projected to fall as snow based on that temperature threshold, and the portion that is projected to fall as rain, again based on that temperature threshold. So for the mountains and for the northern ecozones, our future projections suggest an increase in both snow and rain during November to April, where the foothills and the prairie and parkland, the projections show approximately no change in the amount of snow that is falling, but substantial increases in the amount of rain that fall between November and April. The other thing that's interesting about the cumulative precipitation by temperature is that we can take a look at how much of the precipitation is falling at very low temperatures, which gives us, we can infer a bit of the temperature of the snowpack, or how the dynamics of the temperature of the snowpack might change. And this is important because a warmer snowpack will melt faster than a colder snowpack, because when you add energy to a cold snowpack, you first have to raise the temperature of the snowpack to 0 degrees before it starts melting. So if it's already quite warm, then that energy can just be used directly to melt the snow in general. So just focusing in on one as an example, just for the boreal ecozone. We go. So for the historic period, looking at just -10 as an example, about 60% of the precipitation, or 60 millimeters, fell between November and April when the temperature was below 10 degrees. And this is projected to shift in the 2050s to about 30%, and in the 2080s to about 20%. So we're seeing far less precipitation falling at colder temperatures, which we can infer will lead to a warmer snowpack in the future. So the other metric that we did for precipitation was taking a look at the probability density functions and how that shifts from the historic through the 2050 and 2080s periods. So these graphs have solid lines, which are representative of that total snowfall, and the dotted lines are representative of the total precipitation for each of these scenarios. For each of these curves is the distribution of that for future 30-year climatology, and for the historic period, that 1950 to 2017 distribution. And so in the historic period, the total precipitation and the snowfall are fairly well coupled. So if precipitation was low, snowfall was generally low. If the mean precipitation is, or the high, pretty close to what the mean snowfall is in most of the ecozones. But in future scenarios, there's sort of a general decoupling, and this is consistent with what we saw in the previous graphs, where there's a shift there's an increase in precipitation projected for the future, and a shift from dominant snowfall to dominant rainfall, where some of the ecozones see an increase in just rainfall, and some see an increase in snowfall and rainfall. So just to focus in as an example on the mountain ecozone, we see that the distributions are projected to shift such that historically rare high precipitation and high snowfall amounts are expected to become much more common in the future. So as an example, in the historic period, a snowfall amount of more than 300 millimeters occurred 4.5% of the time between 1950 and 2017. So this is fairly rare. And in the future, in the 2050s, that 300 millimeter threshold of snowfall is much more frequent. This occurs 16.7% of the years out of those 30-year climatology. And in the 2080s, it is 13.3% of the years over that 30-year period. So these higher snowfall amounts are projected to become much more common. This is very similar for total precipitation amount, where historically rare high precipitation amounts over November to April are projected to become just much more common, and these historically rare, very low precipitation and low snowfall amounts just don't even exist in future probability density functions. So basically, this is just changing the range of the potential precipitation amounts. Okay, so trying to get through this quickly so we can get to our break on time. And there's, from this study, there's so much more to show. So for this particular RCP 8.5 scenario, we're projecting novel winter climates in all of the ecozones in Alberta, shorter winter duration, earlier spring onset, higher precipitation, a lower snowfall fraction, and increases in the amount of precipitation that's falling as snow for some ecozones, the mountain and the northern, and the foothills and the southern ecozones. Increases in precipitation are projected to arrive as rain and not as snow. So the variable rates of change among the ecozones is projected to change the climate gradients that we see across the province. So it'd be really interesting to see how that pairs with some of the hydrologic scenarios for stream flow, as well as these shifts in the dynamics of snowfall and rainfall and total precipitation. It would be interesting to see how that translates to hydrologically, what those scenarios would look like. So the mountains, the prairies were two regions that I think sort of went through really quickly, but they emerge as regions of higher magnitude changes relative to the other ecozones as part of that changing climate gradients. And I think it raises a lot of other potential research to take a look at, again, the hydrology, or digging a little bit closer into some of those spring scenarios, and really the identification of the mountains and the prairies, just to help point to where to focus some of the future research just regionally across the province. So many thanks to my team, Babak and John. Got the reference for the paper is listed here. You can always contact me. I'm happy to send the paper. And also, I should say that I'm going to give a much more comprehensive and longer talk at an OCS science seminar in November. So if you're interested in hearing more details about this work, you can join the science seminar. And thank you.
That's great, Brandy, and actually ending just on time, and given the fact you started a couple minutes late, there's probably time for just a couple short questions. I know it's eating into our break, but in fairness, just want to make sure that there is an opportunity for one or two questions.
Yeah, so I got two questions, so I'll go with the first one and see how the time works. With the mountainous change, with the mountains changing faster, will we see plains melt and mountain melt at the same time? This has implications for ice jam flooding and so on. So the basic question is that will we see plain melt and the mountain melt at the same time?
So the spring isotherm timing would suggest that the gap between mountains and plains melt may shorten, but we'll also see some of the changing dynamics in snowpack, and there might be midwinter melts. And so I think this really needs just like a much deeper dive, and certainly for implications for ice jam floods, that's going to be a function of not only the timing of melt, but also the melt intensity, which this study didn't get into at all, and both the amount of snow melt and the amount of rainfall that is coming in early in the season. So I think there's this, it's very complex, and there's no super easy answer, and something that I would love to spend more time working on.
Okay, thank you. So most of those are comments, like thanks for your presentation. Other than that, I don't have any question. Okay.
Okay, I think Carmen just got a question in. I don't know if it's going to be a quick one, so Oh, just a comment, just saying that
It's
we're
a
already
comment,
seeing
so-
mountains and plains melting at the same time in the Upper Milk and St. Mary's, causing infrastructure and transboundary issues in the past 5 to 7 years. So great observation. Yeah, it seems like the presentation really, a lot of people appreciated the delivery and the message. So excellent work. Thanks, Brandy.
Thank you.
Round of applause for all our presenters for our first half session, I guess, of the day. And I guess just to respect everyone's time, and we all probably need a little break and time to get ready for the next speakers, technology-wise. I think I'm going to close this session. I'm just looking at Zahid if I need to mention anything else, or we're
No,
good, right?
I think it's all good. So I'll stop recording right now, and
Yes.
then we can do the testing for the afternoon presenters, and then we can resume recording when we start at 2:45. So
Great.
So,
All right. Thanks, everyone. We will see you at 2:45.